the type C to Langlands people. Login करो लगना है ना? एक बार देखते हैं हो रहा है कितना ऑडियो का पॉइंट उसकी बात ये थोड़ा सा बोल रहा है 5 मिनट इस काम के
It's a microphone.
I'm not going to log in.
Recording solve करता है. Okay. Hello. So on behalf of the Bhaskaracharya Pratishthan and IISER Pune, I am welcoming Professor Murty from Queen's University for this Harishchandra lecture series. And today he will be giving 2 talks. The first talk is right now on the topic, what is an L function? So over to Professor Murty. Thank you very much. Do I put this in the pocket, this one, or do we just leave it like this? Do we just leave it like this? Just, oh, careful there, yeah. Is it okay, this thing? Okay, great. Well, okay, thank you very much. Thanks to Bhaskaracharya Pratishtana and the organizers of this lecture series for inviting me. And thank you for all coming to this talk. So this is a kind of a survey talk, trying to cover at least 300 plus years of mathematics related to the concept of an L function in an hour. And hopefully in the afternoon lecture, you'll have more classical presentation with a Blackboard lecture where things will be a lot slower. So there might be things that go very fast in this particular presentation. So do I have to point this way in order to get this? Or can I just, oh, it's okay. So let's talk about zeta and L functions. A zeta or L function is a Dirichlet series attached to a multiplicative arithmetical function. So 2 words that are key in this sentence, Dirichlet series and multiplicative. By studying the analytic properties of the series, one deduces information about the function. Just like in the classical theory of generating functions, you package the sequence of numbers that you're interested in into power series, and then study the power series. And from that power series, you're able to get formulas for the coefficients. In this case, it's not a power series, but it's a Dirichlet series. Often the L function contains some deep information about the distribution of prime numbers and can be considered as a global object, as opposed to the primes, which are often called local objects. So the concept of a multiplicative function is something that embodies within it the local global principle. That is, the multiplicative function is determined by its values on prime numbers or prime powers. In a profound way, the L function encapsulates the local global principle in a single analytic function. So let's begin with Euler, who first perhaps wrote down the first zeta function. There's Euler. A century before Riemann, he had introduced the zeta function and had studied it and derived even a functional equation for it. But he did not study it as a function of a complex variable, but he studied it as a function of a real variable. And this is where the difference emerges between Euler and Riemann. So beginning with the idea that you have a series summation 1 over n of s, and the fact that every natural number can be written as a product of prime powers uniquely, he was able to derive a Euler, what's now called an Euler product. That means he noticed that the series summation 1 over n to the s is over all the natural numbers is also a product over all primes of 1 minus 1 over p to the s inverse. This allowed him to give a new proof of the infinitude of primes by letting s go to 1. So you see, here's a pointer, right? I think I can point. Let's see. Does this work? Yes, it works. So summation 1 over n to the s, if I let s go to 1, you all know that's the harmonic series, it diverges. If there were only finitely many primes, if I let s go to 1, this converges. So this has to diverge also, indicating that there are infinitely many primes. This is Euler's proof that there are infinitely many primes. Now, interestingly enough, and I remember having a conversation with several young graduate students at IIT Delhi just a couple of days ago, they were telling me that some of their friends frown upon them working on things and trying to come up with new proofs of things. I had to tell them that, look, if you didn't come up with new proofs of things, you wouldn't make an advance. So coming up with new proofs of old theorems is perfectly good research. In fact, coming up with new proofs of old theorems is a way of reinterpreting the whole. Oh, okay. Or should I just stop for a second? Okay. Okay. Sure. Is it not live streaming? Oh, okay. Usually it's easier if you just tape the thing and then post it afterwards. See, this live streaming thing, I don't see the point. Because you're not going to allow those people to ask questions.
They can send something in the.
Oh, in that. Yeah, but the people who are interested can join the Zoom session, right?
Yeah.
Yeah.
So I'm sorry for interrupting, but I am listening to this talk through Zoom and the slides. Okay, now it changed. Sorry, please continue.
Okay. Can I continue now? Okay. So this is a new proof. This is a new proof of the infinitude of primes, and you may frown upon it because Euclid had proved infinitude of primes. What are you doing reproving it? Well, it has to do with conceptual proofs. So certain proofs may be idiosyncratic. Other proofs may be more conceptual and indicate a new direction. This is one of them. This is definitely one of them. This is this new proof. Now this thing isn't working. Let's see. Oh, now my thing isn't working. Would it work if I did this? The thing is not working. Oh, okay. It's working now? Okay, okay. So this idea was later useful to Dirichlet when he showed there are infinitely many primes in any given arithmetic progression. Now, the zeta function has other interesting properties. One of the most beautiful things about the zeta function is its special values. And Euler was, fascinated by the special values. And there was this famous problem called the Basel problem of trying to evaluate explicitly summation 1 over n squared. And he noticed that it actually is pi squared over 6. So he was so happy about this result. And then he generalized it and showed that zeta 2k is always a power of pi to the 2k times some rational number, which is given essentially by the kth Bernoulli number. So this is a famous formula. All of you probably have seen this before. It is still an open problem. of determining explicitly the zeta function at odd arguments. So zeta 3, zeta 5, zeta 7, what are they? Are they powers of pi to cubed, pi to the 5, pi to the 7, etc.? We don't know. So it's an open question. Okay, now it turns out that Gauss had given some thought to the problem of distribution of prime numbers. So there's Gauss. The most precise conjecture on the distribution of primes was formulated by Carl Friedrich Gauss around 1793 when he was a teenager. He was 15 years old. If we let pi of x be the number of primes up to x, Gauss conjectured that pi of x is asymptotic to the what's called the logarithmic integral of dy by log y. And if all of you know how to integrate by parts, if you start integrating by parts, you'll see that the first term is x over log x. Okay, so pi of x being asymptotic to x over log x is often called the prime number theorem. PNT for short. Now, in 1850, Chebyshev showed that there are constants a and b such that ax over log x is less than pi of x less than bx over log x, and that if the limit exists, then it equals 1. Story of Chebyshev is very interesting because he tried very hard to prove the prime number theorem, and unfortunately, all his methods were elementary. And the best he could do using the most elementary of methods, first-year calculus at best, is that he showed that if the limit exists, it's 1. So if that limit, pi of x divided by x over log x exists, it's actually 1, but he couldn't show that the limit exists. So the existence of this limit seemed to be a deeper problem. And it required the development of complex analysis. There was no way you could do it without complex analysis. In fact, if you study the evolution of the subject complex analysis, it was all motivated by trying to prove this prime number theorem. So it's a very interesting how number theory has often been the source of development of other branches of mathematics as well. So now we come to Riemann. Now, in 1859, Riemann wrote his short 8-page paper. That's the famous paper in which he makes the celebrated Riemann hypothesis. How the zeta function can be used to prove the prime number theorem. In that paper, he derived an analytic continuation of the zeta function to the entire complex plane apart from a pole at s equals 1, and established a functional equation relating the value at s to the value at 1 minus s. He gave a heuristic derivation of an explicit formula for the number of primes up to x, with connecting it with the complex zeros of the zeta function. So for the first time in the history of human thought, we see an intimate connection between the distribution of prime numbers and the zeros of the zeta function. That there's an identity between the two. And somehow you had to understand the zeros of the zeta function if you wanted to prove the prime number theorem. So finally, this was done in 1896 by Hadamard de la Vallée-Poussin, who gave a rigorous treatment of Riemann's method and proved the prime number theorem by showing that the zeta function had no zeros on the line real s equals 1. You all know that the famous Riemann hypothesis is the zeta function has no zeros with real part bigger than a half. That's the Riemann hypothesis. If it has no zeros with real part bigger than a half, it certainly has no zeros with real part equal to 1. But you needed that. How does it go? Yeah, you needed that in order to show the prime number theorem. So these are the two people. They proved this result independently. Poor Riemann died of tuberculosis at the age of 40. So in a short span of his life, he did wonderful things, isn't it? Establishing the foundations of complex analysis and number theory. All right, now we come to a very conceptual idea that tells you somehow that the distribution of primes is intimately intertwined with the Riemann zeta function. This has to do with the Wiener-Ikehara-Tauberian theorem. Wiener and Ikehara was Wiener's student, and what they came up with was a nice formula, but they also showed as a consequence of their work that the prime number theorem is equivalent to the fact that the zeta function had no zeros, the real s equals 1. It was equivalent. So remember, in the Hadamard-Della Valle-Poussin proof, they used the fact that there was no zero on the line real s equals 1 to prove the prime number theorem. Wiener and Ikehara went the other way and showed there's no, if you had the prime number theorem, then the zeta function has no zeros on the line. So it's completely equivalent. So this is why in the psychology of mathematicians of the mathematical world at the time, people thought that there was no way of proving the prime number theorem without using complex analysis. And you may know about the elementary proof of the prime number theorem due to Erdős and Selberg. Now that's another story I won't be able to tell, but clearly that was the psychology prevailing at that time. And it all emanates from this particular theorem. So the easiest way to understand the work of Hadamard and Della Valle-Poussin is through the Wiener-Ikehara-Tauberian theorem, proved in the 1930s. Usually this theorem is derived using the Fair kernel and Fourier analysis. Recently, my former student, Aksha Vatwani, who's now a professor at IIT Gandhinagar, and her student Jagannath Sahu and myself gave a very simple proof of this theorem using basic Fourier analysis. It just appeared in the journal Expositiones Math. So here's our theorem. If you let summation b of t over t to the s be a Dirichlet series with non-negative coefficients, and supposing you can factor out some zeta function out of the picture, and if g of s is now a Dirichlet series absolutely convergent for real s bigger than or equal to 1 and not 0 there, then you can immediately derive an asymptotic formula for the summatory function, summation b of t, t less than x. Now, how do you apply that theorem in our context, the proof of the prime number theorem? Recall that Euler had proved that the zeta function can be written as a product over prime numbers. So you have these two different ways of looking at the Riemann zeta function. And now if you take logs of both sides and differentiate what's called the logarithmic derivative, you get this Dirichlet series, summation lambda n over n to the s. And this lambda n function is log p if n is a prime power and 0 otherwise. And it's called the von Mangold function after the person who discovered it. And since the zeta function does not vanish on the line real s equals 1, where is this thing? There. The zeta function doesn't vanish on the line real s equals 1. The left-hand side is analytic for real s bigger than or equal to 1. Except, of course, at s equals 1 where it has a pole. So it's perfect, and these coefficients are non-negative. These coefficients are non-negative, so it's perfect. We can therefore write the left-hand side, whereas this thing, write the left-hand side as zeta s times g of s analytic, apply the Tauberian theorem that was given in the previous slide, and lo and behold, you get what's called the prime number theorem with this von Mangold function, and it's a simple exercise to go from here to pi of x by partial summation. So partial summation argument gives that pi of x is asymptotic to x over log x. So this is how the prime number theorem can be proved. Now, the primes in arithmetic progressions were studied by Dirichlet much earlier than Euler. He started studying them in 1837, I believe. That's Dirichlet. In 1850, he managed to show the infinitude of primes in arithmetic progressions by adapting Euler's proof, that proof that I gave you at the very beginning of taking the limit as s goes to 1. He adapted that proof to show that there are infinitely many primes in a given arithmetic progression. Now, if you didn't have Euler's proof, you wouldn't have been able to build this proof. So this crazy argument that some students are bombarded with, that somehow you shouldn't be reproving theorems known, is stupid. Anyway, so I just want to point that out. Now, in the context of Dirichlet's proof, he came up with these things called homomorphisms from the integers coprime residue classes mod m into the complex, non-zero complex numbers, and these are called characters, Dirichlet characters. And the L functions that he introduced is summation chi of n over n to the s, and just like the Riemann zeta function, he showed that they have an Euler product because it's a multiplicative function. Homomorphism is a multiplicative function. So put it together, you get this summation product chi of p over p to the minus s inverse. So you have this, and Dirichlet also discovered what are called orthogonality relations of these characters. Some of you may have seen this in a basic course in group theory, but this whole chapter of group theory called character theory comes from this, begins here. So just like complex analysis begins with the prime number theorem, group theory begins here. Primes in arithmetic progressions. The prime number theorem for arithmetic progressions now is very simple. After noticing that the linear combination of the logarithmic derivative of LS chi with an application of the orthogonality relations leads to a formula similar to the series that we had talked about, summation lambda n over n to the s, but this time n is now congruent to A mod m. So in other words, the right-hand side here essentially are the primes congruent to A mod m. So you now do the same trick as Euler, take the limit as s goes to 1, and all the characters which are not trivial on the left-hand side turn out to be regular, meaning well-behaved, whereas there's the zeta function corresponding to the trivial character that leads to a divergence of the left-hand side. Therefore, the right-hand side must also diverge. And therefore, there are infinitely many primes congruent to A mod m. So notice in this proof, all you're getting is infinitely many primes. But if you want to get the counting function, you need the Tauberian theorem. So the Tauberian theorem now, the way I formulated it in my joint paper with my two colleagues, gives us immediately this result. So Dirichlet proved that L1 chi is not 0 using Euler's technique, but we need to know that LS chi is not 0 for real s equal to 1. And that's a little harder. And the simplest proof requires the study of the Dedekind zeta function, which we will now describe. So we come now to Dedekind zeta function. So if k is an algebraic number field, and OK its ring of integers, Dedekind showed that every ideal of OK can be factored as a unique product of prime ideals. This is interesting because the analogy is natural numbers, all natural numbers can be written as a product of prime numbers uniquely. Now we move to the world of ring of integers in a number field, and there the prime ideals play the role of prime numbers. So every ideal now can be written as a product of prime ideals in a unique way. This point, by the way, was really at the heart, again, much of this ring theory of algebraic number fields was motivated by Fermat's last theorem. Now, Fermat's last theorem, you may remember, is the assertion that x to the n plus y to the n equals z to the n has no non-trivial integer solutions. Now, Kummer and other mathematicians before Kummer were always churning out elementary methods using natural numbers. And I think there's even a proof by Cauchy of Fermat's last theorem, where he assumes that unique factorization holds all the time for every number field. And that's wrong. So if you look at the integers of a number field, they do not form a unique factorization domain. So you have to move to ideals in order to capture that unique factorization into prime ideals. So this is a big idea. And again, the theory of Dedekind domains begins here, motivated by Fermat's last theorem problem in number theory. So unique factorization theorem holds for OK. And so in analogy with the Riemann zeta function, Dedekind defined the summation 1 over the norm of the ideal to the power of s. And then using his unique factorization theorem, notice that since the norm is a multiplicative function on the ideals, you can write the Dedekind zeta function as a infinite product over prime ideals. So by copying the method of Hadamard and de la Valle-Poisson, one can show that the zeta k function extends analytically to real s equals 1 and does not vanish there. An application of the Tauberian theorem now gives us what is called the prime ideal theorem, namely the number of prime ideals whose norm is less than x is asymptotic to x over log x. So we have a generalization. If you take the special case of k being the rational numbers, then ordinary integers are the ring of integers. The prime number theorem is a special case of the prime ideal theorem, because every ideal in the rational case is principal. So Hecke showed in 1918 that the Dedekind zeta function like the Riemann zeta function, extends to an entire complex plane, and satisfies a suitable functional equation relating its value at S to its value at 1 minus S. Now, Tate's thesis, which you may have heard of, is a Fourier analytic proof of Hecke's 1918 theorem. When was Tate's thesis written down? 1952. What is it? It's a reproof of Hecke's theorem. There's nothing new in Tate's thesis from the standpoint of results. But what do we have here? We have a conceptual insight into how to view zeta functions, functional equations, and the whole theory of automorphic L functions starts here. So there we have it. Fourier analytic proof, representation theoretic proof, actually. So now, in the intervening time, around the same time, early 1900s, Ramanujan had stumbled on, as in his inimitable fashion, come up with what are now called higher dimensional L functions. He gave the first hint that there are L functions of a higher dimension that exist in his own way. He introduced what's called the tau function. Summation tau n q to the n is equal to this infinite product. In other words, if I take this infinite product and expand it, the coefficient of q to the n is tau n. And he made three conjectures, which have become famous, that tau is multiplicative. See that word, multiplicative? Multiplicative. It satisfies a second order recurrence relation like this at the prime powers. And the tau of p is bounded by 2 times p to the 11 halves. And he also, in that same paper, defined a Dirichlet series like the zeta function. So he defined summation tau n to the s, like the zeta function. And noticed that he could actually prove that, where's this thing? Yeah, he actually proved a functional equation. And then if this second conjecture of his is correct, and the first two conjectures are right, he noticed you could write it as an infinite Euler product over primes, but this time the polynomial is a quadratic nature. It's a little more complicated than the Euler products we've been looking at so far. So this is a two-dimensional L function. The first two conjectures were proved by Mordell in 1917, and the third by Dillon in 1974, for which Dillon was awarded the Fields Medal. Again, this is a conjecture that stimulated a lot of research in algebraic geometry, namely the Weil conjectures, H-L cohomology, scheme theory, all the stuff that was all stimulated by this particular conjecture. Mordell seems to have, sadly, missed an opportunity to develop what is now called Hecke theory, since his proof practically generalizes word for word to what are called eigenforms. So I don't want to talk too much about this, but I just wanted to point out that sometimes when we work on things and don't see the big picture, we can miss an opportunity of making a breakthrough. So this is a sad case of Mordell. Now, Hecke's theory, there's Hecke. Hecke's theory of modular forms generalizes Ramanujan's example. It takes Ramanujan's example and puts it in a larger spectrum of more results of a similar nature. And it begins by looking at the modular group, what's called SL2Z, 2 by 2 matrices with integer entries whose determinant is 1. These matrices act on the upper half plane by classical modular transformation. And so functions transforming according to these transformations in this fashion, f of az plus b over cz plus d equals cz plus d to the k times f of z. These are called modular forms of weight k. And the Ramanujan tau function is a case in point where that infinite product was really a modular form of weight 12. And these things have Fourier expansions. And Hecke proved that to each modular form, he could associate a Dirichlet series and extend analytically to the entire complex plane and satisfy a suitable functional equation. But for the series to have an Euler product, it had to be an eigenfunction of a family of linear operators called Hecke operators. And so there's this interesting theory. The multiplicativity of the tau function was a special case in point. Not all Fourier coefficients of modular forms are multiplicative. They have to be eigenforms. of Hecke operators, and the tau function was. And so Hecke figured out that that's the general pattern. This initiated a theory of two-dimensional L series, which was later generalized by what's called the Langlands program. Oops, okay. Around that time, the 1920s, Emil Artin was introducing his non-abelian L series, which was to generalize what Dirichlet had done. So what did Dirichlet do? He took a character of the coprime residue classes modulo M, and he attached a Dirichlet series to that thing. And then he noticed that it had an Euler product, and then established analytic continuation for that thing. Now, the group of coprime residue classes modulo M is the Galois group of the mth cyclotomic field. And by understanding that way, you could see that there has to be a generalization for an arbitrary Galois extension. So this is what Artin came up with. So if you take an arbitrary field, f over k, Galois extension of algebraic number fields with Galois group G, one can associate to each unramified prime ideal. Don't worry about what that word means. Just say prime ideal P. One can associate a conjugacy class called Frob P in the Galois group. And given a representation of G, complex linear representation of G, one can associate an Artin L function. So here again, we have an Euler product, infinite product. You can associate the L series. Now what do we have? We don't have a Dirichlet series and then moving to an Euler product. We're defining the function through the Euler product itself. And this is essential in the Langlands program. So what we have now, Artin conjectured that these L functions extend to the entire complex plane. And if rho is irreducible and non-trivial, the conjecture is still open. But if rho is one-dimensional, Artin proved his conjecture. And this is often called the Artin reciprocity law. Langlands, Tunnel, and Chandrasekhar Khare have shown that if rho is two-dimensional and solvable, the conjecture is also true. And there it sits. I think we have not made any further progress after that. The general Langlands program proposes a plan to prove this conjecture. In some sense, the Langlands program, which is highly representation theoretic, was inspired by Artin's conjecture. Now, in the intervening years, there's a famous theorem in character theory, which I think many are taught, called the Brouwer induction theorem. This says that any character of a finite group is an integer linear combination of characters, one-dimensional characters induced from subgroups. And these subgroups are of a special type. They're actually elementary subgroups. These elementary subgroups are nilpotent groups, and using Artin's reciprocity law and some functorial properties of Artin L series, this implies that any Artin L series extends meromorphically to the entire complex plane and does not vanish there. So you have to use the reciprocity law to show that the Artin L series is analytic on real S equals 1. And so if you have that, now you apply the Tauberian theorem, and you can get a generalization of Dirichlet's theorem in primes and arithmetic progressions. What is the generalization? That the Frobenius conjugacy class are uniformly distributed in the Galois group. So you see, the primes in arithmetic progressions, the Galois group is coprime residue classes modulo M, and you're associating each prime P to a residue class of P modulo M. And you're saying that infinitely many primes are occurring in each class. The same thing is happening here. For each prime ideal, you're associating a Frobenius class, prop P, and you're saying for each conjugacy class, there are infinitely many in that. In fact, the distribution is uniform in the sense of the uniform probability distribution. I may talk more in a general context in the afternoon lecture on this point. So now we come to the Langlands program. Langlands in 1968 proposed a new program trying to understand the work of Hecke and generalizing the work of Hecke. First idea, in this context, he introduced what are now called automorphic L functions, L as pi, where pi is an automorphic representation, which we will shortly define. Now, for those of you who may know, Langlands wrote a very small book called Euler Products, and it's only 35 pages long. Try to read it and say good luck. So it's very dense, it's very profound, and it builds on this whole idea of defining zeta functions using Euler products. In fact, the way Artin did it. He showed all these L functions are entire, so he was basically recasting much of Hecke's work. In fact, he was starting with an eigenform itself, and then interpreting the L function adelically. I will talk a little bit about the adelic perspective in a second, but suffice it to say for now that he managed to show all these L functions are entire, and they satisfy suitable functional equation. And then he says the Artin L series should be there. So he's proved all these families, all these L functions are entire. The question is, are they do they include Artin L series? Are there any technical problems? No. Is there? Oh, pardon me. There's no what? There's no charger. You mean for what? Oh, the computer? Oh. Do I wait for a while?
You can continue.
I can continue. It's okay. 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 So in this way, Artin's conjecture would be proved. Building on earlier work of Gelfand, Fomin, and Harishchandra, he viewed modular forms from a representation theory perspective. His innovation was to introduce the adelic approach and generalize the method of Tate's thesis to GLM. So you see now Tate's thesis, reproving an old theorem, all of a sudden comes to facilitate a new perspective of building L functions from that vantage point. So the idea here now is to take a GLN and look at it adelically. The adels, I will say a few words about the adels, is essentially a pasting together of all the completions of the rational numbers for all the primes, including the infinite prime. Let me just say that here. From modular forms to automorphic representations. So first thing is you had to go back to the world of classical modular forms and reinterpret that in geometric terms, topological terms. So to each modular form, one can actually associate phi sub f on a certain symmetric space. And the details are very simple. If I have a group acting on a set S, and if the action is transitive, that means you give me 2 points, x and y. There's an element group in the group taking g x to y via g. That's called transitive action. If that's the case, then I can identify the set that it's acting on as a coset space. G modulo gamma sub x, where gamma sub x is a stabilizer of any point. It doesn't matter. You can take any point. So in other words, a group acting on a set S, if the action is transitive, I can identify the set as a coset space. All of a sudden, the set has acquired a richer structure. I can interpret the points of the set as cosets. That's the key, one of the key ideas. Once you have that, then you can interpret the upper half plane as a coset space. See, in the classical theory of modular forms, you have functions on the upper half plane transforming in a certain way. Now, if you're trying to generalize the theory of modular forms, first question is, what's the generalization of an upper half plane? The answer is, if the action is transitive, in which case it is, it's a coset space. So it's SL2R modulo K, where K is the stabilizer of square root minus 1. So I interpret that way, and then I started reinterpreting modular forms as functions on this space, which are left invariant by another discrete subgroup. And in this fashion, I can reinterpret all the whole classical theory of modular forms as functions which are square integrable functions on some coset space of this type, satisfying these properties. So this idea, by the way, this is due to Gelfand and Fomin and Harishchandra. These are the three people that started to reinterpret classical theory of modular forms in terms of representations of these Lie groups. And the innovation of Langlands in his short 35-page book is the shift to the Adele ring. So the field of real numbers, I think all of you know, is the completion of Q with the usual metric. If you take the usual metric and you complete the rational numbers, you get the real numbers. But the usual metric is only one metric. You have all these p-adic metrics. Why did you prefer the usual metric only to the p-adic metrics? You should take all the p-adic metrics and you should not show favoritism to any one of them. So we can endow Q with the p-adic metric, one for each prime, complete Q with respect to that thing, and then you get the field of p-adic numbers. And now a famous theorem of Ostrowski says that these are the only ways of completing the rational number. So now what do we have? We have a new interpretation of the concept of a prime. See, prime numbers are not numbers which don't have non-trivial factors. That was a Euclidean view, fine. But the modern 20th century view is a prime number corresponds to a valuation or a metric on the rational. Each of these things, you get the p-adic numbers, and then when you put it all together, you want to put it all together in such a way that the new ring is a locally compact topological ring. And that's really the explanation why you have that funny adelic topology. You know, you may see these restricted direct products, elements in the thing, but after a while, they have to be p-adic integers. Why did you put that extra condition? It's not just a direct product. It's this extra condition that you put it in so that you get a locally compact topological ring. Once you have a locally compact topological ring, you have a Haar measure. You can do integration. You can do Fourier analysis. And that's the setting for Tate's thesis. And that's the setting that Langlands uses for his generalization into automorphic representation. So we have a Haar measure on this ring. Tate's thesis is that Fourier duality in this ring is at the heart of the functional equation for the Dedekind zeta function. So why should we study Adeles? Well, the question of determining all the characters of the rational numbers has to do with Adeles. Remember, the brilliant idea that Dirichlet came across is the notion of a character. So now, once you have that idea of character, you can study the idea of a character in the large. And if I ask you, what are all the characters of the group, the multiplicative group of the rational numbers? The answer is Adeles. Those Adeles give rise to, and of course, you have to check when they're same characters. You have to quotient out by the Q. And you can embed the rational numbers in the Adele ring just diagonally. You take a rational number x and just put x in all the places. Since the rational number x has only finitely many primes in the numerator and the denominator, after a while it'll become a p-adic integer. So it is an Adele in the true sense of the word, and therefore it turns out that the character group of Q is isomorphic to AQ mod Q. This work of Dirichlet and Hecke fits neatly into this framework, and this is what John Tate did in this famous PhD thesis. So the Adele framework works well for the Langlands program too, and L series attached to automorphic representations have been continued analytically to the entire complex plane, and they satisfy a functional equation. In all cases, the coefficients of the associated Dirichlet series are multiplicative functions of a single variable. Multiplicative functions of a single variable. Now the key word here is not Dirichlet series or multiplicative functions, but the single variable is the key word here. To go beyond this realm, we need to study multiplicative functions of several variables. Now, the first person who seems to have started this theory is Vaidyanatha Swami. So several mathematicians have proposed how to generalize the notion of a multiplicative function to several variables. But it seems that in 1928, Vaidyanatha Swami is the guy who first came up with the correct definition. What I say is correct is the definition that's conceptually powerful that allows for generalization. So how do you generalize a multiplicative function of several variables? Do you say, I fix one variable, it should be multiplicative of the other, and I fix this variable, and it should be multiplicative, in that sense? And people did that, and that's the wrong way to do it. And it seems that Vaidyanatha Swami came up with the right idea. His idea is that if you, he set up some notation, which is very interesting. start off with a function, k variables, use vector notation as much as possible. So instead of natural numbers now, we will talk about k tuples of natural numbers. And divisors, instead of divisors, we'll talk about k tuples of divisors, which will divide component-wise. And the number, the function 1 is simply the one that assigns 1 to everywhere. And then the classical Mobius inversion formula and the classical Mobius function can be generalized to the k-tuple context. And I believe it's Vaidyanatha Swami who proved this Mobius inversion formula here that we have. So one of the things that you would learn in elementary number theory course is if I took a multiplicative function f of d and I added that over the divisors of n, the new function is still multiplicative. This is something that you would learn. And it turns out in this multivariable context, with this definition, it turns out to be correct. That generalization turns out to be correct. A function is multiplicative if f of m1 to mk, f of n1 to nk is f of m1, n1 to nk, mk, nk, provided that the m's and the n's have nothing to do with each other. There's no common prime factor. That's the definition. Sometimes coming up with the right generalization is hard. So anyway, we have to give credit to Vaidyanatha Swami who did that. And now an example of a two-variable multiplicative function is the Ramanujan sum function, the Ramanujan sum. So Ramanujan sum is defined as c cube n summation e to the 2 pi I a n over q, where a and q are relatively prime. So this is a function of q and n. And if I fix n, it is a multiplicative function of q. But if I fix q, it is not a multiplicative function of n. So the old style generalization of multiplicative function wouldn't work, but it is a multiplicative function of two variables in the sense of Vaidyanatha Swami. Okay, so you have that. And another way of writing this thing is CQ of n is summation d divides q and d divides n, mu of q over d. And recently, several problems have emerged regarding Ramanujan sums that can only be solved using the theory of Dirichlet series of several variables, and we will describe two of them. So now, just as I told you at the very beginning, the Tauberian theorem was needed in order to prove the prime number theorem. If I had multiplicative functions of several variables, and if I wanted to get asymptotic formulas for summatory functions in so many different constraints, how am I going to do it? You would associate a Dirichlet series, which is a function of several complex variables, and then have to analyze that. So in the classical setting in 1932, Carmichael showed that these Ramanujan sums have a certain orthogonality principle. So if you took one Ramanujan sum CR of n, and you took a shift CS of n, then there was an orthogonality principle that is very important in number theory. If R equals S, it spits out another Ramanujan sum. Otherwise, it's zero. So this is a very profound tool. And in joint work with Sinha Chobe and Shivani Goel, we studied triple Ramanujan convolution. So if you took three of these things, until we started doing it, no one did this. If you take triple convolutions, and you can actually show that this is zero. Now, in this paper that we wrote, we derived the result using elementary methods and not the theory of multiple Dirichlet series. And if you try to do this with higher convolution sums, these elementary methods will not work. And so for higher convolutions, we have to adopt a different method. And in recent work with Shivani Goel, we viewed the problem from the vantage point of multiplicative functions of several variables. So recall that we had these results. The question is, if I took higher and higher convolutions, how do I analyze this sum? It turns out that this limit actually exists, and this is a multiplicative function, and it equals this, what looks messy, but it's not. What is this g function? G function is equal to 1 if the system of congruences has a solution and 0 otherwise. So it's basically the Chinese remainder theorem issue. Now, you all know that the system has a unique solution modulo d1 to dk if all the di's are mutually coprime. But if they're not mutually coprime, they may not. It may have a solution, may not have a solution still. So, but it is interestingly enough that this is a multiplicative function in general. So we use that. And the second problem we can apply this theory to is to find the asymptotic behavior of these higher moments of summatory functions of the Ramanujan sum. And in joint work recently completed, we showed that this function has this complicated behavior. Notice that there's a certain x to the k, but there's a polynomial in log x, which comes out. And to prove this, we need to use the Tauberian theorem for multiplicative functions of several variables due to British. This particular problem was studied earlier by Anthony Robles and Arindam Roy, but they made a fundamental error, and they didn't have the right formula. In fact, they stated a wrong result, which, well, it's wrong. That's all there is to it. So the British-Tauberian theorem is you have this Dirichlet series with a non-negative function. This time it doesn't have to be multiplicative. Non-negative function, f of n1 to nk, n1 to the s1, nk to the sk, and then you have to have it satisfy certain conditions, which I'm not going to go into in the interest of time. But let me just flash these things in so that people can see them. Some technical conditions you have to kind of check. And under all those technical conditions are satisfied, then it spits out a nice asymptotic formula. So the question is now, in our context, we have to do that. So in our context, what turns out that this function that we were interested in is a product of zeta functions. But now these zeta functions are not just functions of single variable zeta, s1 plus s2 plus s3, and so on and so forth. So you know the zeta function has a pole when the argument equals 1. So it's no longer a single point, which is a singularity, but it could be a subvariety. That's the problem, and that's what the British-Tauberian theorem handles. And once you have that, you can happily go and solve the problem. So may the Himalayan sages inspire our minds to greater heights. That's the Himalayas. Thank you for your attention.
So it was a very nice talk, a survey from the times of Euler to the very recent times. So if you have any questions, comments, you are most welcome. Anybody has a question or comment?
Yes. Yep.
The theorem in the first line, is there an analog of Perron's formula? Or
An analog of what?
Perron.
No, Perron's formula is still one variable.
So it does not have a generalization in
Multivariable, no. Well, you can try to generalize it, but it's not the same thing.
is it possible or it's not possible?
I think people have tried. It's horribly hard.
And then if you take powers of zeta function to the power of k, you take zeta function to the power of k, and then you have a Dirichlet series representation where the Dirichlet coefficients are dkn, the number of is to write n as a product of k natural numbers. So what is an analog of that when you take powers of L function?
Same thing, kth power of the thing. I don't understand. What was the analog of what?
So if you take zeta function and you take raise it to the power of k,
Yeah.
and then you can have a nice representation in terms of Dirichlet series where the Dirichlet coefficients,
Yeah.
they are the function dkn.
Okay, so you're saying if you took a when you say L function, which L function are you talking about? Dirichlet L functions or Langlands L functions?
Dirichlet, yes.
Oh, then that's very easy. That's an easy answer. It's just chi of n times dk of n. Times dk of n. Ls chi, you're going to take Ls chi to the power k.
Okay.
The coefficient turns out to be dk of n again times the Dirichlet character.
Nice. And what about Langlands? What about powers of Langlands L function?
Oh, they'll be more complicated. That's the point. They will not be divisor functions. Because you see, the divisor function is coming only because the Euler factor is one-dimensional. If you have higher dimensional things, it'll be all messy. Just as in the case of modular forms.
So the coefficients would be the function dkn multiplied by its character.
In the one-dimensional Euler product case, but in the higher dimensional case, it'll be more complicated functions.
can you still apply the method of contour integration to that?
Yeah,
and,
yeah. The method of
find the
contour
symmetric
integration is general. You can apply it. Yeah, you can apply
you
it.
can find the
Yeah.
symmetric function.
Yeah, you could do that. I mean, that's, of course, you need to know analytic properties, whatever, but the method of contour integration is universal. It says you can apply it and you'll get results, provided you know the analytic properties and you can estimate it on those contour. Yeah, yeah.
Yeah, any other question or comment? Yeah. Okay, so if not, then we thank Professor Murty for this nice talk, and then we will meet again at 3 o'clock for the second class. Thank you.
Because I can get rid of this now, right? Did the microphone work? Did this come through? This microphone? Thank you.